All right, our next speaker will be Tobias, who will be talking about ephemeral network layer fingerprinting defenses.
Thank you very much. Yeah, so I'm Tobias, and this is work together with Topi, Ethan, and Niklas sitting here in the front. So yeah, I'm going to talk about ephemeral network layer fingerprinting defenses. So for defenses, we obviously need some attacks, yeah? And as luck would have it, we just got a good introduction to website fingerprinting attacks. If you think about website fingerprinting attacks, it's a local passive adversary that looks like a connection to Tor, to NIM, to a VPN or something like that, and tries to figure out a website, right, that's being visited. A website visit takes something like a couple of seconds, if you're lucky, depending on the performance of the network and stuff you're using, right? And we're talking about a couple of thousand of packets that have to be sent, yeah? Of course, website fingerprinting attacks are in scope for us, but we also look at other dimensions. If we go to the smaller side, we have circuit fingerprinting attacks. Here, the goal of the adversary is to determine what kind of circuit the user is using when connecting to Tor. And typically, this involves trying to find if the user is visiting an onion website or a regular website. This is done by looking at the first 30 or so cells and, you know, a handshake in the handshake of Tor. And this takes something like a couple of 100 milliseconds, maybe. Then, to the more extreme case, we can go to video fingerprinting attacks. For a video fingerprinting attack, the goal of the adversary is to determine what video a user is watching at the video service, like YouTube, for example. And of course, if you think about video traffic, it can be from seconds to minutes to hours if you're watching a movie, right? And a lot of data. So these three attacks have a wide span of in space and time, how much data adversary has to deal with. And in our case, they're all three in scope. The question that led us down this road in this paper was that what if every connection has a unique defense? We've been spending a lot of time building, you know, custom-made individual defenses, but what if every connection had its own defense? So in a sense, defenses were ephemeral, like ephemeral keys when you have in TLS and the like, right? And the first contribution towards this direction was to find a way to find a lot of defenses, because that's what we need, right? If they're ephemeral, we need a lot of them. So we designed a ephemeral defense search algorithm. And it's in 4 steps. I will give you the high-level intuition here. So first, in the first step, what we do is we use a defense framework called Maybe Not, which is a framework for traffic analysis defenses, where defenses are expressed as probabilistic state machines. So we use Maybe Not here when we create random defenses as a domain-specific language. And by that I mean that if you create a random state machine in Maybe Not, the probability of this thing being a good defense is higher than if you create a random Python program, for example, right? Because we're constrained to the domain we're in. So the first step in our search is to just create random state machines, a lot of them, and have state machines running on the client side and on the relay side, or server, depending on the setting you're in, yeah? And these together make up a defense, a candidate defense. Then in step 2, we take the candidate defense and we simulate the candidate defense on a bunch of network traces that represent the task we care about. Mostly we do it for website fingerprinting here. And we do it in a very fast network simulator, the Maybe Not simulator, and we use diverse network conditions here. We simulate different network conditions, yeah? Then we look at the resulting simulated traces and we assess them if they fulfill some constraints we place on these traces. The constraints we place are mainly around bandwidth and latency overheads. That's it. The defenses that come out of that, those we accept. Then we move on to step number 3. So in step number 3, we have a bunch of defenses now that fulfill some constraints in our environments that we used in step 2 to simulation. We then take these defenses and we rip them apart. As I mentioned, they're composed of machines running both at the client and the server side. So we make a pile of all the client ones and a pile of all the server ones. Then we randomly combine them. And we also add up multiple machines on each side. So you can have, for example, 3 state machines on the client and 2 on the server. Then we consider this as a new candidate defense and we repeat this process again. As luck would have it, it turns out that if you take the components of a defense that fulfills the constraints from step 2, if you arbitrarily combine them, most of them still fulfill the constraints, oddly enough, as luck would have it. That means that we now have a way to get polynomial growth in the number of defenses we have. We can create a lot of defenses very quickly. And the last step is then deploying these defenses, for example, using the Maybe Not framework and integrations, and then you get tunable bandwidth latency overheads because it's built into the Maybe Not framework. For this search process, there is some tuning involved with machine and environment parameters, but time does not permit me to go through this. So let's carry on. How well does this thing work then? Well, we start with website fingerprinting attacks. And here we use the big enough data set and a bunch of related work. We took related work and implemented it in the Maybe Not framework as state machines and did our very best to hyperparameter tune this. I see that Nick is smiling now because I spent so much time on regulator. It's horrible to tune. But anyway, thank you for that. So yeah, we tuned each defense for 2 scenarios with infinite network traffic, which is basically how, infinite network bandwidth. That's usually how we simulate things in the community. We also did it with a simulated network bottleneck between the client and server. Yeah. So then we had a bunch of defenses, and we classified them on the left side based on if they're padding-only defenses or if they're also defenses that had latency through blocking actions. Yeah. Then we assessed them in terms of their overhead on the far right side and the accuracy for 5 different attacks, representing 3 generations of deep learning-based attacks. I just want to highlight Laserbeak here, which is the state-of-the-art attack, according to me at least. What we see here from these results is that the ephemeral defenses, the padding-only ones and the blocking ones, are competitive to related work. They're on the Pareto front with different trade-offs and so forth, right? So okay, that's website fingerprinting. The ephemeral search works pretty well here. They're not stellar, they're not beating by far the related work, but they're pretty good. They're on the same side, yeah? Then we moved on to video fingerprinting. And here we take the ephemeral defenses for website fingerprinting, tuned for website fingerprinting, and use them as is. The same defenses, yeah? But now we use them for video fingerprinting instead. Here we use the long enough data set. The long enough data set comes in the default version and 4 bandwidth constrained with variable bandwidth versions in them. And we compare the ephemeral defenses in the bottom with the state-of-the-art custom defense scrambler in this setting. What we see is that, okay, scrambler, a custom tuned defense for this setting, of course, it does better in terms of accuracy. It offers better protection, yeah? It's close to optimal. Ephemeral defenses do pretty good though. And especially where they do pretty good is if you look at the overhead side. We see that the ephemeral defenses are not very sensitive. They don't really care that much about the network environments. That's a huge win. Moving on to the smaller side of things, we go to circuit fingerprinting again. There's no good related work to compare to here because most related work, or we're not aware of any related work that works for circuit fingerprinting currently. So we can compare our tuned defenses for website fingerprinting, the non-tuned ones for website fingerprinting, and the one we tuned for circuit fingerprinting. As a reminder here, we're targeting the first 30 cells of a handshake. So overheads of like 10 times bandwidth just means 300 cells. It's not a lot, yeah. And it's binary classification here, so 50% is the baseline. What we see here, once again, is that the website fingerprinting defenses do pretty good here as well. They're not as good as optimal, but they're still pretty decent for this task as well. Oh, spicy. An error exists on this page. Okay. Adobe Acrobat Reader does not like my favorite picture of the entire presentation. So my favorite picture on the presentation, it's a good cliffhanger for the poster, because it's in the poster, I hope. Yeah. So on the poster, you will be able to see a beautiful heat map, where what we did is that we took Laserbeak and trained it for as long as it required for it to finish, which was a very long time. It was an expensive experiment, but super fun. And what you see is that we trained a model then for every defense we had, and then we used that model to test on every possible defense as well. So you get this matrix where the diagonal shows you where you train and test on the same thing. But what you can see from this beautiful heat map soon, when you come to the poster, is that the ephemeral defenses, when you train on that with a state-of-the-art website fingerprinting defense, the attack learns to generalize. It learns how to attack a wide range of other defenses because it's trained on the diverse defenses of the ephemeral ones. Super cool, most fun result of the paper, in my opinion. Talk more about it at the poster. Yeah. So to wrap up, what we did in this paper is that we set out to search for ephemeral defenses that are only used once per connection, ideally, and we investigated what this means in different settings. What we found mainly was that for website fingerprinting defenses, when you use the ephemeral defenses there, they're multi-purpose in the sense that you can get ephemeral defenses that are not really tightly tuned to any particular type of attack or data set or network conditions. So they're kind of a bit general purpose. They're pretty good in general for most things that we tested at least. This system has been deployed in a version of it soon for 2 years with Mullvad VPN in production with the data feature, which is an opt-in feature there. Also, the underlying framework, maybe not, is integrated into RT. Rust's Tor integration. Sorry, no, Tor's Rust integration, implementation. Life's hard. Perfect, 10 minutes. Thank you very much. Oof.